So, what is that question that was asked in the last, just before we are disconnecting? The
Yes,
electronics
ma'am.
question that ma'am was looking. What is that? Can you repeat, Vishnu?
Yes, ma'am. Actually, I had to clarify it. I wasn't specifying about I initially asked about why registers are so fast. Actually, wanted to ask why are caches so fast, ma'am? Because
Compared to,
because now we're observing that the amount of memory we can store in caches is also increasing to a point where it's not non-trivial anymore. We are able to store in the order of hundreds of megabytes. There are some special processors, but if we are approaching a size where if we're approaching such a large size of cache, does it make sense to cache like that again? Because I don't know whether the quality of the silicon is the same in between just normal DRAM and the caches present on the PC, or is it completely different?
even I
This was
need
my
to check
question
about
actually.
that regarding the
So
quality of. Mm.
the difference is that caches use what is called as static RAM, SRAM.
Yes, ma'am.
Okay. Whereas main memory uses what is called as dynamic RAM.
DRAM, yes, ma'am.
Okay, so the dynamic RAM requires constant refresh
Yes, ma'am.
to keep the value. Okay, it's a volatile memory,
Yes,
right?
ma'am.
So, but even in volatile memory, it requires a constant refresh to keep it going. Static RAM, once you have written it, it doesn't require this sort of constant voltage refreshment and all that. Actually, I was reading some article, okay, some amount of knowledge I picked up. This is the topic that I have actually removed from the schedule recently, yesterday night, because I thought it's difficult. But what we can do, what I did at that time was when I taught, because I realized it was very difficult for me to understand what's there in NSE and Patterson. I asked my brother-in-law to talk about it. So we'll see if we have time, whether we can make either my brother-in-law or Chakravarti sir, somebody who is good in electronics, to talk about that.
Okay, ma'am.
Because it does require understanding of the electronics to an extent. And so I was also looking at, I found one nice blog for register itself. So anyway, the answer for the registers is they are directly connected to the ALU on the chip. Okay. So they are very, very fast because of that, because they're just circuitry. Literally, they are just circuitry on the switch, on the chip with the ALU. So this
There's no
blog,
latency.
yeah, so there is absolutely nothing they need to do. So he does explain in this blog a little about from the hardware, from the electronics perspective, that it doesn't even have a capacitor, whereas, you just set the transistor. You people did EDC, if you remember that, maybe you will understand, because I have forgotten my EDC. Sorry, it's way too long since I read EDC. I don't mind reading it again now, but since I haven't read, they talk about that they just directly connect to the transistor in the case of registers, whereas they have to do the transistor capacitor when it talk about any of the ramps.
Okay.
So that slows down things. And so if you look at the memory hierarchy, in fact, the next chapter is where we should be discussing this. We'll see that as the cost goes up, the speed goes up. So, and the size therefore goes down. You are right when you say that caches are very large today, but compared to your RAMs, they're very small.
Yes, ma'am.
Okay, so that's the short answer. We'll talk about that when we come to memory hierarchy more. So.
Yes, ma'am. That was also, ma'am, because like my perception of why I felt the caches were small was to reduce the search space. So, ma'am, when the process trying to retrieve some instruction from the cache, if it's small enough, that means our search time is also smaller, hence it's faster. So,
Yeah, it
so
is
that is
true.
why I didn't understand why are we going big on cache.
Well, the still the hit time will not be as badly affected because they do a parallel lookup.
Okay.
So,
All right, ma'am.
um, so let me just talk about addressing mode for control instructions, which is where I stopped in the before the break. So I said this is called PC relative addressing, right? What do we mean by that? We are using immediate addressing or displacement addressing with respect to the program counter. Okay, so we add certain amount of offset to the program counter to go to the branch target instruction, right? So the branch is successful and it wants to go to the function, let us say. Then, the function starting address is defined with respect to the PC, not in absolute terms. This is essentially what the control addressing mode that is used if the distance from the program counter is small enough, because again here you have about 16 bits or so for the offset from the program counter. So therefore, if your function is within 64 KB of your current program counter, then you can use it. If it is larger than that, then you have to do something else, right? This is the addressing mode for control instructions. Now, on the other hand, when you talk about procedure call and return, how many of you have seen the procedure call and return um, in the videos? Because he has explained so beautifully there the jump and link instruction and jump return instruction, which are there to implement a procedure. Okay, if you have not seen, please do see. And it's actually very, very nicely described in the videos. And you will see, if anyone who has seen the videos will realize that the return from the instruction procedure, right, is through the register 31 contains the return address from the procedure. So because why is it that this is not part of PC relative addressing? Why can't we somehow, okay, you jump to the procedure, right? Okay, you are executing some statement in main, and then you get if I equal to 0, call function f1, right? So if you say if I equal to 0, call f1, when you say I equal to 0, then when you come to call f1, it is using the command jump and link, right? Command that MIPS in the MIPS instruction set architecture, that the which is the example architecture throughout this book, as well as the videos that I have posted. So you are using PC relative addressing. So you'll say F1 is located so many bytes away from my main function. We are not saying any absolute address where F1 is located. We are saying it is located with respect to the current program counter. Okay. Now, but to return from F1, okay, when you return from F1, normally you return to the instruction immediately following the call to F1 in the main, right? But it can also happen that you may call some other function which may exit the program. Okay, you never know at compile time what is going to be the return from a function, because you don't know whether the function is going to be successful or unsuccessful, or it goes to some other function and then exits from there from the program. You have no idea. Okay. So because of that, you cannot use PC relative addressing for return, and therefore they use a specific register to store the value of the return address in case you need to return back to the calling program. This is basically, so there are two possibilities in addressing per control instructions. One is the PC relative addressing and the other is to use specific special registers to hold the register target instruction value address. Okay, that's about that. Any questions? So the next thing is the procedure call options, right? And again, this was very, very nicely described in the videos. What is caller saving and callee saving, right? Okay, I'm going to talk only about the principle. He talked very specifically about the MIPS in the video, right? But what we are going to talk about here is the principle behind this. And he gave very beautiful examples for the caller saving and callee saving. When do you do it? When do you not do it? And so on. So just to reiterate what is there, the principle behind it. When you call a function, okay, you are executing something. Okay, so you are using the general purpose registers for your computations, and then you call a function. Now, it is possible that that function will also use the same registers. Why? Because the number of registers is obviously limited, being the highest, in the memory hierarchy, fastest, therefore the costliest. The number of registers is not like infinite. It is very, very finite. Okay. So you may have to reuse those registers. And we know what is called, context switch in operating systems. What is context switch? What do we do as part of context switch? One of the first things we do as part of context switch.
We store the state of a process and
So what is the state? Yeah, what is when we say context of a process, what do we mean? What's the context of the process?
like values which are uh, you know which are processed and
Sorry?
uh, like after a few operations the values which are generated and like they are stored.
Yeah, those values generated may be in registers, right? Normally what is happening, you are executing the process, then you get an interrupt.
Yes, ma'am.
Okay, it's not like you have finished storing from the registers into memory. You are still actually in the process of operation. So there are, of course, interruptible instructions, non-interruptible instructions, and so on. Whatever. The point is that you have not finished your instruction probably when you get an interrupt. So the registers are having your current values, which are not yet stored back to the memory. And they may be needed for doing certain amount of work. So what do? Essentially what you do is you save the contents of this register into the PCB. That's what is the context switch part, right? One of the things you do as part of context switch is to save the register values into your process control block. And when you run again, you restore them from the process control block into the registers. Okay. So similarly, when you are calling a function, okay, there may be registers you are already using and those values are there, and you will continue to use those values in a later instructions after you return from the function. Now, on the other hand, the function may also need to use the same registers because there are not enough registers. in which case it will overwrite the values of the calling function. So this can be a problem. Now the question therefore becomes, who saves these registers? Should the caller save the registers, or should the callee, that is the called function, save the registers? This is a question that you have to answer as part of your instruction set architecture. Okay, MIPS answered it in a specific way. If you look at the videos, they have very clearly, the videos clearly state that there is a set of registers numbers from here to here, which are saved by the caller. If there are values in registers from this number to this number, they are saved by the called function. Okay. And when do you save? You only save if you are going to write to that register, not otherwise, because when you don't do any work which is not necessary to save time. So, there is a very well-defined convention in MIPS which says do this, caller does this, callee does this. Okay. All processes may not solve it the same way, but we have to solve it in some fashion. That is the point here, right? And, one of the problems is that we'll be seeing this again in the memory hierarchy, but there is something called the concept of aliasing. What is aliasing? You have, an integer variable I, okay? You define a pointer to it, and then you say star p equal to something, right? So now I may be stored in one register, star p may be stored in another register if you don't know that they are both referring to the same variable. Okay, this is what is aliasing. Okay, they are, in some sense, you think you are referring to two memory locations, but you are referring to the same memory location. These sort of things create a lot of problem for both register allocation, saving of registers, and we will see other issues which crop up when we do memory hierarchy. Okay, so you need to be aware, and C is the only language which probably does a lot of such funny things, but it does it in the interest of speed. So the compiler has to do a lot of work to ensure the correctness when you do these things, right? Okay, I think we are probably having only another 10 minutes of time. So let me just talk about encoding of the instruction set architecture. So you can have fixed encoding, which means that every instance is of fixed length. The length is fixed, it cannot change. Okay. So 19 minutes are left. How? I thought in mine it says 12:52. Our class is up to 1 o'clock, right? So
No, he's saying for the session to end.
Session may end at some point, man, but your class is up to 1, so we'll do only up to 1. Okay. So when you can have fixed length instructions. Okay. What is the advantage of doing fixed length instructions? It's actually very, easy to do pipelining with these instructions. When you do go for that sort of a instruction set, it's very easy to do pipelining. What's the disadvantage? The disadvantage is that you will have to generate many instructions, and whether or not you need that many bits in an instruction. See, for example, I may actually need only one operand in my operation for whatever reason. Okay. But I have space in my instruction for 3 operands, right? Like if you take the MIPS instruction, format, it it allows you to, it's basically a register operation, but with 3 operands, where there is a result operand and 2 source operands. And some of the architectures may actually use 2 operand architecture, where one register is both the source and result. Anyway, so you have, if we take the MIPS architecture, it always says 3 operands. We may not need 3 operands for all the instructions. So we are unnecessarily wasting space for 2 operands there, which makes the code size larger. And so that is one of the disadvantages of fixed size instruction length. Now, variable instruction length will mean that you have, some instructions. In fact, example given in the book is of the Intel x86 architecture, where the smallest instruction in Intel is 1 byte long and the longest is 17 bytes long. Okay? Whereas MIPS is always 4 bytes long. Advantage, however, is that you will get smaller size of the executable code with a variable instruction set, because you are only using as many bits in your instruction as needed. However, different instructions take different lengths of time to execute. They also have, very, very different ways of accessing memory. So they support a large number of addressing modes, in which case you cannot encode the addressing mode in the opcode itself. So remember, we said that we can encode both operation and addressing mode if the number of operations and the number of addressing modes are small. Then in fact, MIPS uses only 6 bits for the opcode and is able to support 3 addressing modes and small number of operations in that. Why is it successful? It is successful because most of the operations that we see in the world use these addressing modes and use only these operations. All the other operations that other architectures came up with are not frequently used. So now you look at your Amdahl's law that ma'am talked about in the last class. It says you should optimize the most common case. So they made the entire instruction encoding in such a way that these operations and these addressing modes are very easily decoded and, very fast, so that the entire operation execution time becomes very fast. So the variable, instruction encoding will basically mean that you have smaller size of the executable, okay? But the problem with that is different instructions take different amounts of time for execution, especially because some of them will have a very weird addressing mode. So they have to have an address specifier, which tells you how to, actually calculate the address, effective address, and then from there to go and fetch the operand. So all this will, take a lot of clock cycles and different clock cycles for different instructions. And this is not amenable to pipelining. So overall, your program runs smaller because it's unable to take advantage of advanced techniques. Okay, that is the thing. And then you therefore have some hybrid architectures which are not completely variable, but they are not completely fixed either. And PowerPC is an example of such architecture. Okay, so that is basically what you need to know about encoding. I'm not talking beyond that because, in the videos, he has talked in a very detailed fashion about the I instruction, J instruction, R instruction formats of MIPS. Please do be familiar with them, because please note the rest of this textbook uses MIPS as its example architecture to explain all the various functionalities and algorithms used, techniques used to speed up the processor. So you have to get familiar with the instruction set of MIPS. Any questions on whatever we have done so far? Because the next thing is, how do compilers and architectures interact with each other? And I just want to ask this question. I'll take, I have listed optimizations used by compilers here. I know that you didn't complete your compiler's course, but are you familiar with these terms?
Some
Okay.
I know loop unrolling and allocation of variables to registers and graph coloring.
Yeah,
And the
in fact,
expansion of procedures, and I think you only specified it during programming methodology. Like whenever we had like a smaller function.
yeah,
So the
macros, what we define as
macros.
macros. Yeah. But even if you don't specify some function as inline, please note that even in Java, you have what are called as inline functions, right? When you are specifying something as inline function, definitely, the compiler will expand it. When you define a macro, the compiler will expand it. However, the compiler may also make some intelligent decisions on its own. Okay, when you're doing optimizations. And I think some 3 people sent me, results of the code they wrote that I asked you people to write. Using -01, -02, and -03 optimization levels of GCC for insertion sort with large number of values. So the observation was without optimization and with optimization, obviously the time reduces. I also, however, wrote to all 3 of the people that when we use -03 optimization, sometimes the results may not be correct. I wanted them to make sure that the results were correct. And I think the observation was that sometimes they did not get the correct results with -03 optimization. It's a very interesting, observation. And so we usually use only up to -02 to ensure correctness of the results. Anyway, the point is that when compiler is doing smart optimizations on its own, it may expand some of the procedures to be in line, okay, but it doesn't know in advance what's the size of the procedure. So its decisions are, complicated because once this inline expansion happens at the very, beginning of the optimizations that procedure that a compiler does. So if later it finds that there are problems with that, it cannot unroll that and it cannot roll back those optimizations. So it's very difficult for the compiler to figure out whether to expand inline or not. Anyway, we did not talk in length, but I hope you remember that we just mentioned in passing, and Kanigan and Richie talks about that you can declare a variable to be register variable. Now, when you say something is a register variable, essentially you are giving a hint to the compiler. I talked about this to you people, but at that time it wouldn't have made sense. It will make sense now. I hope that it gives a hint to the compiler to put this variable in the register and not remove it from the register. Not remove it meaning don't use this register for any other purposes, right? So it's something like, fixedly mapping the variable to the register. Why? Because this variable is going to be used so often that even if you push it to the cache and back from the cache, it's going to affect the performance of the program. Having it in the register means that you don't have to load and store. You're constantly using it. So it really speeds up your program. That's, so which variable should you allocate to registers? This is the question that the compiler needs to ask itself. What variables shall I, allocate to registers? They are usually, obviously, only local variables. Arrays and all are not allocated to registers. Pointers are not allocated to registers because of the aliasing problem that I talked about. So usually they are variables which are on the stack which come into registers, right? So that's the sort of discussion that the book talks about. So we'll continue it in the next class, right, about this and other issues regarding compilers and architectures. Okay. So any questions? In the discussion forum of instruction set principles, which says discussion session on Tuesday, I'm posting this blog article about why registers are fast. Just for information I'm saying. Okay, any questions?
Ma'am, like in the videos, he talks about using a stack for the procedural calls.
Right. I know. In fact, in replying to you in the forum, I said we'll discuss it in the class. So in the next class, we'll do it.
Okay.
Because there is a lot still to talk about the compilers and this one, and I'll also talk about how that stack thing works. It actually relates to your OS also. So
Okay.
we'll look at it from both OS perspective, which is where we would have come across that. And in fact, I haven't talked about some aspects of the register indirect. Where is it exactly used and things like that, which relate to again OS. I'll maybe take it up in the next class because I don't know how well you remember your dynamic linking and dynamic loading and things like that. So we'll do it in the next class.
Okay. Okay.